roughness, and what fraction it is, you need to have some data in this region to know. What if you just plot roughness height, you get different lines, they all have the same slope, and if you just now apply the correct ratio, you can make them all collapse. And then we refer to sand grain roughness for convenience. The only problem is we need to have at least one point in the fully rough regime, and we need to know that for sure that we're in the fully rough regime to know how much the ratio of Ks to K is. So in the end, we are left with the same problem of predicting delta U plus if we want to predict Ks plus. And this is, it's not a closed problem. What we have in general is correlations, and you've had a taster of that on Wednesday and a bit on Thursday. These are 4 pages of correlation from a recent paper in AIAA from Daniel and Karen Flack. Same thing in a graph would look like this. This is from their annual review, okay? And the problem is there are families and families, and there's always a new roughness geometry that doesn't fit into the correlations, and you have to find a new correlation for a new family. More modern approaches to these are machine learning. Shervin presented this work. It was essentially this yesterday, right? And it's just fitting data with neural networks, etc., and trying to be predictive about this. There's another work that I think is pretty nice from Junlin Yuan's group, which is also machine learning. For me, this is still trying to fit data and correlate, so it's some kind of glorified least squares, okay, at least in this context. And if I was doing this, I wouldn't find it completely satisfying. I'm in this job for the fun, not for the money. So I want to learn about things, not just get values of what CF is going to be, okay? So what I'm going to propose is let's try to understand how there being a surface that is not smooth is modifying the flow. Because the elephant in the room here is that roughness is not a property of the geometry, or not exclusively, it is a property of the flow, okay? And you can see that just by looking at the transitionally rough regime. In this region, the delta U plus that you get, how would I explain this? Maybe better, if you want to reduce the effect of your roughness to geometry, getting your Ks is going to be enough. It turns out that as you go into the transitionally rough regime, if your Ks is expressing a value of delta U plus, if it's just a currency exchange as in its original sense, then your ratio of Ks to K is not fixed. So it's not a geometric parameter. It depends on the Reynolds number if you want. It depends on the flow, okay? So my approach is let's try to understand what's going on with the flow, okay? And because I'm underpinning what I'm going to talk in the second part is this idea of virtual origin, so I felt I needed to talk about this a little bit. This is what happens, or it's a theory that describes what's going on when the textures are very small, okay? So these are basically Paolo's protrusion heights. I'll be talking about what they are in a second, but you can think of this as a number that is proportional to the roughness size or the texture size, okay? And then when it's very small, textures lie in this linear regime, okay? And that's Paolo's linear regime. And I've just put data here from a bunch of surfaces that we've worked on in my group. These are drag reducing surfaces, and they stay longer in this linear regime, and that's good because that's what gives you the drag reduction. Roughness, this is a particularly harsh example of roughness because it's a very tall, intrusive roughness, a canopy. But roughness in general tends to peel off very quickly from this virtual origin regime, unfortunately, okay? Okay, so what's the idea of these two parameters, stream-wise protrusion height, span-wise protrusion height, if you want? This is something that was proposed by Paolo in the 90s. He started looking at this in riblets, and he argued that the riblets obstructed more the stream-wise flow than the span-wise flow. Eventually, after 5 years, he came up with a way of phrasing this, of connecting this to how it modifies turbulence. And essentially, the idea is that if you have some reference plane, and this could be, for instance, the tip plane of your textures, the highest point of your textures, compared to if there was a smooth wall at that plane, your flow is going to have in the mean some slip at that height. And because these are small sizes, you can extrapolate linearly into the substrate and find where the velocity would become 0, and then you can refer to a virtual origin for the mean velocity. it's the same as the slip velocity if you're talking in wall units, okay, because this slope is 1. Now, what Paolo argued is there is a similar effect for the crossflow, and who induces crossflow in near-wall turbulence? Quasi-streamwise vortices. So if you now have a slip length on the quasi-streamwise vortices, they are going to be displaced down because they can live in harmony with non-zero span-wise velocities at this plane, so they can go a bit closer to the wall, okay? And then he argued that there would be a delta U plus, which would be proportional to the difference between those two, something like this. And this mu0 Daniel talked about yesterday. I think Paolo proposed a 0.7 early on. Javier did some analysis that gave him a 0.6 a few years later, or a few years before, whatever. And then, Paolo, you changed to a 1 around 2015.
Complicated story.
Well,
it took 4 years to be published.
Okay, so what I would argue that this has to be a 1, okay? And the reason is given by Paolo in his paper in '96. This was never pushed further, but it's literally here. You expect turbulence to be sitting on this plane. So turbulence compared to a smooth wall is exactly the same, except the origin is here. And that means everything, including the Reynolds stresses, has the shape it has over a smooth wall, just starting in this plane. So from here on, the curvature of the mean profile is going to follow the Reynolds stresses, so it's going to be like over a smooth wall. And any depth additional to that that you have before you reach 0 in this linear extrapolation, that's extra flow rate that you have compared to a smooth wall flow. And how much is that? If the slope here is 1, this distance is going to give you the delta U plus. So this mu has to be 1. But the key thing here, and that's what was never chased by the rest of the community, is that the origin for your turbulence, for your statistics, for everything should be the origin apparent for turbulence. And on top of that, you just have a Galilean translation from whatever is different in the origin for the mean profile. Okay? Yes? They can, and in that case, you would have 0 drag reduction. And if LU plus is higher than LW plus, then you get a drag increase. Because by the time U starts being non-zero, it's already curving up as if a smooth wall be 10 wall units above the, well, 10. This is really for small sizes, okay, for 3, 4 wall units, or things like that. Okay, so let's do this, okay? If you look at the classical flow control drag reduction literature, you'll see plots like this, where as you increase your texture size or your control intensity, you get changes in your RMSs or in your Reynolds stress, and then people start arguing the streaks get closer to the wall or the vortices get stronger if there's a change in omega. But this is all measuring your fluctuations, etc., from your reference plane, from your tip plane, or from your control plane, whatever it is. And following literally what Paolo said, I'm going to use an axis that has the origin at that y plus LT plus equals 0, or y plus equals minus LT plus. Oh, there's just one thing for the mean flow here. I've subtracted the streamwise slip so that all the graphs start on the same point. And then people would argue that this is the roughness effect induced by the spanwise slip. Once you've removed the streamwise slip, all the effect you have is the spanwise slip, and then they would say that it changes the flow farther away. What happens if I plot this with origin at the virtual origin for turbulence? It looks like that, okay? So turbulence is smooth wall-like, okay? The mean profile is parallel throughout to a smooth wall profile. The only problem is that it starts at some height that is already non-zero, because the 0 was virtually deep inside the substrate, okay? So I don't have data for the most intense thing here, the red, below this point. But once I start from my y0, which is already 4 wall units above the virtual origin for turbulence, it's perfectly parallel. And then if I subtract my theoretical delta U plus that I would expect, which is 1 times that difference in slips, I get exactly the same result, okay? The only difference that you can see here is in U prime, and well, I'll comment about this later, but basically, if you have a virtual origin for the streamwise velocity that is deeper, this flow is not forced to come to 0 at the same height, well, this velocity as the others. It has a bit more of a gap, so it has a slightly more intense peak also coming from that, but there's no additional effect on top of that, okay? Okay, I thought Paolo had solved this problem, and it was just delta U plus is Lx plus minus Lz plus, whatever you want to call them, and that was that. But then when I started looking into superhydrophobic surfaces, there's some data, and this is a particularly nice data set from Angela with Neil Sandam, where they tried very large slips in both directions. And then they saw that something that has the same slip in the streamwise and the spanwise, which according to Paolo's theory would have 0 change in drag, eventually would have some change in drag, okay? And it's like the spanwise slip effect saturates. So even if you increase the spanwise slip, once it's large enough, you don't get any additional degrading drag. That would be the effect of the spanwise slip, okay? And in a hand-wavy way, we argue that that's the case because streamwise vortices approach the wall when you introduce some slip length in the spanwise that is small, but if you keep increasing this, eventually the vortex would not want just a tangential velocity at that plane, it would also want to induce some wall normal velocity. And if at this plane you have v equals 0, you are not letting the vortex approach anymore than in this regime where LW plus is much smaller than, say, the distance between the vortex and the wall. Once curvature effects would want to kick in this region, you would need a V to accompany your W to let the vortex keep going any deeper, okay? And empirically, we could capture that effect by using, instead of a spanwise slip, a degraded spanwise slip, which basically asymptotes to 5, okay? So once you get to 2, 3 wall units, this is no longer giving you a 2 or 3 effect, and by the time you get to 100, it just gives you 5, and 200, it gives you 5, okay? And then if I plot all this data from Angela as a function of LW plus minus, it's now not the spanwise slip of Paolo, but this degraded one, then it all falls in a straight line, okay? The only points that don't, these are at very low Reynolds number, and I believe these simulations were run at constant flow rate. So yes, so I suspect that these ones had such a low drag, such a low RE tau that they were relaminarizing. The dynamics are different for those, okay? But the same slips at higher Reynolds number would not relaminarize and fall on the line. Okay. So we wanted to check if we could recover vortices penetrating without desaturation if we allowed transpiration to go together with tangential slip. And then we thought for a while on how to allow for that. We played, well, first we started just imposing virtual walls for all velocities at some depth, and then we would do 3, 4 wall units of Stokes flow analytically and impose that as a boundary condition for the overlying flow. We tried a bunch of things. In the end, the one that worked easier was to impose also a Robin condition on V, okay? And the only caveat here is that this Robin coefficient is no longer the virtual origin for V, because V, as it approaches the wall, is quadratic. And then the origin for V, well, what we do is we look at smooth wall data and say, okay, we want a virtual origin for V that would be accompanying our virtual origin for the spanway. So 4 wall units. So at 4 wall units above the wall in a smooth wall, what gradient do I have? Then I would need just 3 wall units of Robin coefficient to get a virtual origin in V of 4, okay? And we actually do this for all 3 velocities, but the effect is larger for, well, it's very strong for V, weak, very weak for W, and almost negligible for U. And this is why I've been talking about LU, LV, and LW. Those are the origins for the velocities instead of the Robin coefficients, which are especially different for V, okay? Now, if we allow transpiration to penetrate like spanwise velocity, it turns out that the virtual origin for turbulence is not saturated. So we can let the vortices go in for depths further than 4 wall units or 5. I commented on having slip on the streaks having no effect, and we went up to infinite slip on the streaks, and that has no effect on the Reynolds number, no effect on the peak of omega. So we are arguing that this is an inactive effect. The vortices are really the thing that's driving turbulence near the wall, and then if there's more gap for flow to be brought in or to be extracted, then the U prime signal will vary a bit, but that will not affect otherwise turbulence. And there's a paper that Javier has just put on arXiv saying that streaks are not an essential part of the near wall cycle, which I would advise it. It's a bit mind-blowing, but when I saw it, I thought, oh, well, that could explain this. Okay. I've shown the RMSs, but if I show you the spectra, it's the same thing. It's collapse, collapse, collapse. If I measure at a height based on the virtual origin for turbulence. Okay, so this is where the peak of the near wall cycle would be, 15 wall units above the virtual origin for turbulence. Okay, and then we could put everything together into a single equation that tells you that if there's any virtual origin deeper for W than for V, that extra depth is going to operate in this saturated regime. Okay, if the origin for V and for W goes together, then that will be the origin for turbulence. At least for these small values, if you allow an Robin coefficient, an origin for V without allowing it for W, the vortices will not go in, because the first thing that they want to do is to induce a tangential effect. So if you allow just transpiration, there will be nothing happening. Okay. Eventually, this whole thing breaks down once you set very high coefficients, Robin coefficients, or depths for the vortices, and that's because your boundary condition starts ingesting the vortices, and you're no longer just exposing the near wall cycle to offsets. You are actually interfering with it. You're being very disruptive, and then turbulence is no longer smooth wall-like, and I'm not even sure that this is physical. Okay, now you would really need to look at what the actual texture is doing. Okay, so just to wrap up, I've described what happens in this regime. Okay, one nice thing of this regime is that you can calculate these slip lengths based on the idea that the overlying flow is very large compared to a vanishingly small texture, and then you can use homogenization to find your slip lengths. If you want transpiration, you would need to go at least to second order in your homogenization, but this will give you the behavior in that regime. Okay, now what I wanted to talk about. Whoa, okay, so let's see how I do this. Okay, we were very lucky that we looked at this in a texture that is a toy model for superhydrophobic surfaces that has posts with no slip and free slip regions. That means that V is 0, and I think up to any order, homogenization gives you just Robin conditions for U and W. Young-Min Seo and Ali Mani had looked at whether slip coefficients make sense when you check in fully resolved DNSs of this texture, and they found that for small textures there is a good correlation between U du dy at the wall and W dW dy, but once you go to even 10 pluses in spacing, that's not true. And that makes sense, because homogenization is based on the idea that you're expanding in a parameter that's your texture size compared to your flow thickness in laminar flow, but in turbulent flow, that's the smallest eddy in the flow, and that's going to be 15 wall units. Okay, so it's not surprising that what homogenization would tell you doesn't work once you get to those sizes. When I saw this, I thought, but larger scales in larger eddies should still see a homogeneous slip. So maybe instead of doing this in physical space, we should look at this correlation in Fourier, and we did, and it was a mess, and that got us thinking. Eventually, we thought, okay, the problem is that you have a boundary condition here, which is a set of steps multiplying a velocity. This propagates into the whole wave number space. So this signature of the slip no slip is corrupting all your slip lengths. Okay, there's two flows here overlapped in a sense: the texture-induced flow, which goes non-zero, zero, non-zero, zero, and then an overlying turbulence, which would be over a much larger scale if there's a good scale separation. Okay, that would look like this. This is actually roughness, and very close to the wall you can see the footprint of the texture. Okay, and I'm interested in thinking of what happens to this flow, which is the one that has that filtered out. And the traditional way of doing that is triple decomposition, where you do the ensemble average, and then you're left with the texture-induced flow, and then the rest would be the turbulence. But that's what I would want, but it turned out that when I did this and subtracted the ensemble average, and that's done here, here's the raw signal. This is just one cut of this data. Here's the raw signal, here's the ensemble average. You can see that it's a much smaller wavelength. If I subtract this ensemble average from the full signal, I get this. And that's because I've subtracted very little in some regions and too much in others. And then what we proposed from looking at this, and it actually makes sense if you think of Paulo's idea that the overlying flow is inducing a flow nearby, then this flow is going to be intense depending on how intense the flow above is. So the background turbulence modulates in amplitude the texture-induced flow. And then when we introduce that, then if we subtract this amplitude modulated flow, we get a flat, well, a smooth signal. And that's what we understand is the background turbulence. So we can separate this flow algebraically. If there's good scale separation, you can do this in Fourier with filters. But if there's not, if there's some overlap, this will get you some way, okay? And this is actually a complicated relationship between all three velocity components, but just to simplify, looks like that. Now, another interesting thing here is that the ensemble average looks a lot like laminar steady flow, okay? There's comparison here from ensemble averages from DNS and laminar simulations. So you would have a good surrogate for this ensemble average without doing the DNS with a laminar steady flow, at least in this range of sizes that I'm thinking about, K plus less than 50, say. Okay, now, if I subtract that texture-induced flow and I look at the correlation on the background turbulence, it looks like this, okay? And this is up to texture sizes of order 90. We got bored of looking because we weren't, that's the range that we're no longer interested in, okay? So this tells us that it vindicates or reinstates homogenization. The correct boundary conditions for this flow, even for texture sizes that are huge and where homogenization would not be justified, is a slip length. Fine, let's impose this slip length on a DNS without texture and see what happens. And what happens is that when your texture size is 20, things still are fine. But when your texture size is 40 or 50, the flow is different. And now is what I'm going to say is that the reason for this is that this flow is not obeying Navier-Stokes anymore, okay? So with homogenized boundary conditions, you get, as I was talking in the first part, smooth wall behavior. When you do texture, you don't get smooth wall behavior. Your Reynolds stresses are higher in this region near the wall. And one of the reasons we were lucky by checking in this V equals 0 texture is that the Reynolds stresses are 0 at the wall. If we had done this on roughness first, we would have been very confused because this signal would be propagating into this region, and then we would think that it's something that's coming from the wall and propagating into the flow. But this is not. This is something that is floating above the surface, okay? And well, once we have the decomposition, oh, my parentheses have moved. If you plug in whatever decomposition you're doing into your Navier-Stokes, and I'm doing the simple case here of standard triple decomposition, you're going to be left with an equation for the background turbulence. I'm eliminating the terms from the ensemble average because that satisfies essentially Navier-Stokes on its own. Okay, so I could subtract the terms from for the ensemble average equation, and then the equation for turbulence is Navier-Stokes plus these forcing terms, which are the cross terms from the advection. Those have to go with something, right? And they end up being in the equation that governs the background turbulence. And so we thought, okay, let's do a DNS with magical terms that are not part of Navier-Stokes. And we did that. And well, the difference that you have in delta U plus, by the way, between fully resolved and homogeneous leap is here. And when we did that, here are the results. So this is homogeneous leap. This is a fully resolved DNS. The dashed line is if we introduce the forcing terms that I just wrote, the ones without amplitude modulation. And we tried that first because it was easier, and it didn't get us, it got us some way into where we wanted. But then we tried what we thought was the thing to do, which is with amplitude modulation. The equations look more complicated, but these are still terms that you can add. And then it's right on the money, okay? Better than I would have been happy with, but I'm not going to complain about that. The other one is a different texture. So we tried this with a couple of textures just to see that it was not a fluke, okay? And it's the delta U plus, okay. Why am I putting this here? Oh, yeah, it starts failing at some point, okay? But I don't think we're interested in getting this right beyond, say, 60 pluses, because that's roughly where you are already into the fully rough regime for roughness. So if your texture-induced flow is size order 60 and all this framework works up to there, you have at least one point in the fully rough regime. And from here on, I have no idea what the physics are going to be like, but I do know what the behavior is going to be like. So if I can capture all this region with this forcing without resolving the texture, I've solved the problem. I still need to do a DNS, and that's the next step. Can I do this without doing a full DNS? Okay, but at least it's not a DNS that needs to resolve the texture, and that's 100, 500 more points than in a smooth wall DNS. And the rest is just statistics. to show, well, these are snapshots which are meaningless, but statistics to show you that it's not just the delta U plus that you're getting right, but everything in the turbulence, okay? So homogeneous slip is very far from fully resolved, which is at the bottom. Eventually solid blue, which is amplitude modulated forcing, starts deviating, but this is the range where I don't mind if it starts deviating, okay? I wanted to capture things up to there, up to 40 or 50, or no, sorry, 50 or 60 more. RMS fluctuation, same thing, there's a very good collapse up to this region. Spectral densities, okay, you can see that if homogeneous slip looks a lot like smooth wall, well, I'm not plotting smooth wall here, but you'll have to believe me, it's missing a lot of wavelengths. And this forcing is triggering those wavelengths that wouldn't be there. Without amplitude modulation, it's trying to drive the flow there, but it doesn't have quite the wealth of Fourier modes to do that. The amplitude modulation, what it does is it distributes things in, rather than having just the harmonics of the texture, you have more wealth in your signal, in your amplitude modulated signal. Okay, I'll leave it there. I've already run over time, sorry. I'm happy to take any questions if there's time.
Yeah, I think we have time for one quick question. Stefania.
Hi, Ricardo, nice talk. I was wondering, well, I see that your roughness size in the last part, in the superhydrophobic part, is very large. Have you checked if in these conditions with your Reynolds number and Weber number, your gas pocket remain within the roughness? I mean, you're wet and stable or not? Because if you have these changes, maybe it's because it's not realistic case.
I probably didn't explain well. So what we're doing here is an academic model which people use for a superhydrophobic surface. But for this problem, the only thing I'm concerned about is that it has texture, granularity. But it is V equals 0, so Weber number is infinite. Okay. And whether that is a good model or not, but I've done work on interface deformation, okay? But that's when I was worrying about what superhydrophobic surfaces do. Here, it was just a very easy texture that induced V equals 0 at the wall.
Okay, that's right. So it's just an academic, a theoretical.
Yes, absolutely.
Perfect.
And the nice thing, maybe I didn't emphasize that enough, is that isolated the effect of having V and therefore also Reynolds stresses already at the wall. And it was clear that it was something floating in the flow, not something in the boundary condition. And that's what made us look into the governing equations rather than the boundary condition.
Okay, perfect. Thank you.
All right. Oh.
And you saw it was not as bad as not obeying Navier-Stokes, right? It's just a couple of forcing terms. Actually, with amplitude modulation, it's more complicated. It's like the whole advection is
Can you just briefly comment on where those extra terms came from?
Okay. Sorry, then I started to rush because I realized I was pretty late. So for this case, I think it's very easy to see when there's no amplitude modulation. If you just plug U equals U plus ensemble average plus incoherent part, and then, well, there's something similar for the pressure. You just plug it into the equations and then try to separate things. And then there's an equation for the mean flow, and that one has dispersive stresses and turbulent Reynolds stresses. There's an equation for the background, sorry, for the ensemble average, which is essentially Navier-Stokes. And then if you subtract those two from the total, the cross terms are left. So, you have Navier-Stokes for flow A, Navier-Stokes for flow B, but Navier-Stokes for A plus B has advection of A times B. And if flow A satisfies Navier-Stokes of A, then I can cross out all the terms that only have A's. And then I have the terms that have flow B and the terms that have flow A and B mixed.
The terms that you want, you're going to circle in red there. Yeah. If I I see, no, UT. I see.
So it's actually linear in the background turbulence. It's ensemble average, which is pre-computed time UCUT.
I see. Sorry, okay.
But it's actually more complicated. It's not as pretty when you have amplitude modulation, because amplitude modulation makes already U ensemble is non-linear because it's the product of UT times.
So these are from modified capital U. I can see where they come from now. That's confusing.
Okay.
Okay. In the interest of time, there are more questions, but we postpone the discussion. So thanks. So the next speaker is Professor